Hey everyone, in this video we're going to be looking at series and parallel circuits, what they are, how voltage and current act within them, possible advantages, disadvantages of series and parallel circuits, and how resistances combine in those circuits as well. It's going to be largely based on the online software that I've used before, the PhET. If you type in PHET electric circuits into Google, you should get to where you need to get. But I will guide you through it and show you some example circuits that we can have a go at. But really, it's really important, I think, that you have a play with this, because with electricity in particular, this topic, it's a tricky one to understand what's going on, but the PhET really helps you to understand and see visually what's going on. So let me just get the... So the first thing I'm showing you here is a series circuit. Okay, we want to look at the difference between series and parallel circuits. And I'll give you some notes in a second, but the thing to remember about a series circuit is that the electrons can only flow in one loop. If I close this switch, you can see that those electrons or those charges are flowing. Of course, you need a complete circuit. With any circuit, for electricity to flow, you need a complete circuit. Another thing you can play around with this, with the PhET here, is that you can see which things, it's kind of a bit key stage 2y, but you can sort of put objects in, dollar bills, coins, erasers, and just see which ones conduct electricity, which ones are going to allow a complete circuit to flow. But for this particular video, we're just going to talk about series and parallel circuits. And in this case, you can see there was only one option that only one route or loop that these coulombs could move. And for that reason, we would call this a series circuit. Now, a really important point about series circuits is that current is not used up. Okay, I've talked about quite a lot this idea of current being like the flow of a river or the flow of air through a straw. It's not going to go anywhere. As long as you're within that circuit, that air is going to stay flowing through that straw. That water is going to stay flowing through the river. And so you're not going to get more coming out than what you put in. It's an absolutely key point. Don't forget that when we're measuring current, we use ammeters, and these ammeters need to go in series. Okay, so they need to be part of that flow. These coulombs or these electrons are flowing through this current, through this ammeter, and then they are moving. I seem to be moving the wire, so I'll have to. They're going to flow through this resistor, through this resistor, through this ammeter. But notice here that what's really important is that that current there, 0.45 amps, is exactly the same as the current there. Now on this PhET, you can use these ammeters which you put in series. I put them in series here to show you how you would do it in the lab, how you would need to set it up. But with this PhET, you can also use this current meter. It's not really such a thing in real life, but it's really handy to see what's going on, because if I put this current meter here, I can see that just as those coulombs are leaving the battery, I've got 0.45 amps. Anywhere along this wire, it's still 0.45 amps. I go through this resistor. No current has been used up in going through that resistor. It's a flow. Flow doesn't get used up. So it's still 0.45 amps all the way through this. It's 0.45 amps. And in a series circuit, that's exactly what will happen. Anywhere in that series circuit, the current is the same. And everyone seems to know that. Everyone does get that. But when you're doing questions, people sometimes forget that. Okay, have that in your mind. The current in a series circuit is the same anywhere in that series circuit. But we also want to talk about voltage or potential difference. And potential difference, of course, is, we think back to its very basics in the first video we looked at, it is the amount of energy supplied to each of these coulombs, or the amount of energy used up by each of these coulombs. And so it is, as the name suggests, a difference. when we're measuring that, we need to use a voltmeter, and we need to use a voltmeter in parallel. In other words, across the component that we're measuring the potential difference across. That sounds like a bit of a mouthful, doesn't it? But if I were to put this voltmeter across this battery, or in parallel, as we'll see what parallel means in a second, but you can see that effectively what's happening is we've got these coulombs, which effectively have no joules per coulomb, so they have no energy, but this battery is providing, or it's transferring chemical energy into electrical energy, and so by the time they come out here, they have 9 joules each, 9 joules per coulomb. So the difference between this point and this point is 9 volts. Okay, they have to be put, these need to be put across that component, because otherwise you can't tell a difference. You can't just say, what is the potential difference at that point? It's a difference between 2 points. So I can measure the potential difference between 2 points across a resistor. And in this case, what I've got my battery providing 9 volts. And so anywhere within this circuit, I can see here that anywhere across here, I've got 9 volts potential difference across that battery. No work is being done, no energy is being lost as they go through those ammeters. But a resistor, the whole point of a resistor is it's resisting that current. And so work has to be done. Energy has to be transferred to go through a resistor. So I can look at it a slightly different way, and I can say that between this point and this point, those coulombs have had to work to get through those resistors. If I go through one resistor, then some work has been done by that resistor. Remember, these came in, they had 9 joules per coulomb. And now they're doing work through that resistor. And so these are going to have lost some. Assuming these resistors are the same resistance, then they're going to have lost half of the energy going through that resistor. So of that 9 volts, then 4.5 of those volts have been lost by this resistor. And now I can check what the voltage across this resistor is as well. And it's also going to be 4.5. So the total energy lost between this point and this point is 9 volts. The bottom line, and the takeaway, the key takeaway from all of this, is that that voltage has been shared. Okay, that voltage, that potential difference that was 9 volts here, has been shared, in this case, equally, because these resistors are the same. If they were not the same, they would be shared unequally. But the key point is that whatever the voltage supplied by the battery is going to be shared and should add up in total to all the potential differences across the devices in a series circuit. As ever, I always say, have a play with that. Add more resistors, see what's going to happen. But that's your key takeaway. So let's get some key point notes down. So, series circuit. Circuit components are said to be connected in series if the same electric current passes through each of them in turn. There is only one single loop that current can flow. Here's an example. You've got 2 lamps in this case in series with each other and in series with a battery or a cell there. And the first thing we said was that the current is going to be the same throughout that circuit. It's not going to go down, it's not going to get used up. The current is the same in the whole circuit. In this case, 3 amps. It's useful actually just to look at the AQA specification here. Obviously, it's relevant for all boards, but the AQA specification I think words it quite nicely. Components connected in series, there is the same current through each component, and then we talked about, when we looked at that FET, the potential difference of the power supply is shared between those components. So just to reiterate that, whatever this voltage was, let's say it was 12 volts this time, whatever these components are, they would be shared. It might be that they were shared equally, 6 volts and 6 volts, so they add up to the 12, or it might be instead that one of these batteries has, let's delete that, they might have a different resistance. If these lamps were different resistance, then maybe they'd be shared slightly differently. Maybe you'd have 2 volts here. If you had 2 volts here and you had 12 volts here, you would know that they must add up to that 12, so you would know that must be 10, and that's quite a common question. Okay, if you know the voltage here, you know the voltage here, these two must add up to that total potential difference. So that's how it works in a series circuit. Also, a few advantages of series circuits. The main advantage is that you can control everything within that circuit with one switch, and that can be useful. It's not normally particularly useful, and actually we'll see the advantages of parallel circuits are a bit more pronounced. The disadvantages of a series circuit is that if one of these lamps breaks, then no current is going to flow through that. Again, it might be worth having a little play with the effect. You can see that. You can make one of the lamps break, and then the flow through that circuit is not going to work. So that's a big deal. Okay, when I was younger, Christmas tree lights always seemed to be connected in series circuits. So if one of those lights on the Christmas tree broke, the whole lot went. Why they did it like that, I have no idea, because now they're almost always connected in parallel, as we'll see in parallel circuits. If one of them breaks, that lamp will go out, of course, but the rest of those lamps will continue to work. A possible advantage, as I said, is that if you wanted everything to be controlled by one switch, then series circuit is the way to do that. The other thing to be aware of here is that, of course, if I close that switch, I can turn those lights on, as I just said. They will share that energy, and so they will get less bright as you add more lamps in. You can add more lamps into that series circuit, but they're sharing that potential difference. They're sharing that energy per coulomb. Potential difference is energy per coulomb. So as you add more lamps, they're going to get dimmer and dimmer. Brighter when you've got 2 of them, dimmer when you've got 3 of them. Probably a disadvantage, I would say, that you generally want those lamps as bright as possible. Okay, now we're going to look at parallel circuits. Again, I've made this parallel circuit here. It starts to get quite complicated, but you can see here that the currents, let's see what we've got. I've actually added 4 ammeters here. And it starts to look a little bit complicated to see what's going on. I can turn my switch on, turn it off. But a really important thing to realize with the FET is that although this isn't, as I've said before, a real device that you can use, but for the purposes of this demonstration, it's really handy to use this sort of current probe, and I can see what's happening to the current throughout that circuit. So what I'm going to do is I'm going to turn that switch on, and well, using the ammeters that they've given us here, you can actually see pretty much what's going on. You've got a flow of current. In this case, you've got 1.8 amps going here. And the rule about parallel circuits is that whatever goes into this junction, you can see there's a junction there, like a road junction, whatever goes into that junction is going to equal whatever comes out of it. So I've got 1.8 amps going into this junction. If I've got 0.9 amps coming out of it, I must also have 0.9 amps coming out of the other one. So these 0.9 plus the 0.9 must equal 1.8. And I can play around with my probe and check that that's the case everywhere. It's 1.8, 1.8, 1.8. If I go down here, I've got 0.9. And anywhere along this single branch, everything along this single branch would be in series. Yeah, there's only one route that this can take. So everything along here, if I added more light bulbs, which of course I would go at, everything within that branch would be in series with each other. Yeah, these ammeters, we always talk about these ammeters having to be connected in series. These this ammeter here is in series with this lamp, but this ammeter here is in parallel with this ammeter here, because there was a choice, there was a different route that those electrons could go down. So we would say that this lamp is in parallel with this lamp. So with the current, it's fairly straightforward. You can kind of make sense. You can see that flow, just as I've talked about a lot, the idea of a river, whatever's going into that junction of a river is going to be coming out. Potential difference potentially causes a little bit more difficulty when it comes to parallel circuits. If I measure the potential difference across this battery, of course that is the voltage, the energy supplied by that battery. Now, when we've got ammeters, we're assuming there's no resistance in an ammeter. Ideally, an ammeter has no resistance, so no work is being done as I go through that. No energy is lost, so there's no potential difference change. Okay, I've still got 9 volts provided by that battery. If I wanted to know what the potential difference between these 2 points are, I might say they've got 9 joules of energy each. Of these coulombs have got 9 joules of energy here, 9 joules per coulomb, and at this point I've still got 9 joules of energy. So the difference is 0 volts. These 2 points are in series. There is no choice to be made regarding which way these coulombs are going to travel, which way this current is going to flow. But the thing to be aware of when we're talking about parallel circuits, as opposed to series circuits, is that I've still got my 9 volts across these 2 points. So the voltage between this point and this point is still 9 volts. And I'm still doing no work as I go along this wire, so the potential difference between these 2 points is also 9 volts. In other words, what I've got here is 9 volts of energy across, 9 volts of potential difference across the battery. I've also got 9 volts across this lamp, and I've also got 9 volts across this lamp. So it seems slightly counterintuitive that in parallel circuits, the voltage is the same across each branch, each loop. Within this series, which I talked about, within this series line, if I had a different component, then this 9 volts would be shared. If I had another lamp here and another lamp here, these are in series, so this 9 volts would be 3 volts, 3 volts, 3 volts. But in the actual parallel loops themselves, those voltages are going to be the same, and that often causes a bit of difficulty for people. As I say, for this particular topic, the best thing you can do is to play around with this FET. Okay, it's a hard thing to do in a lab where you're playing around with all these components, but this FET software is so useful just to get a good feel of what is happening. But in terms of what do you need to understand and what do you need to be happy with, what do you need to make sure you have as your general rules, here they are. Parallel circuits, the circuit components are said to be in parallel if the circuit has different branches and the current can split into more than one path. Okay, so it's not just going one route like a series circuit, it can go one way or another. At a particular junction, the total current into that junction is going to be the same as the total current coming out of it. So if I had a current, maybe 3 amps going into this junction, and I had 1 amp going here, then I would know this must be 2 amps. This plus this must equal that. So here's one example. We've got, when it comes to potential difference, we've got a voltage here. Let's say that's 9 volts. And so the voltage between these 2 points is still 9 volts. So the difference between this point and this point is still 9 volts. And the potential difference between this point and this point is 9 volts. These voltmeters are the things measuring those. And they also need to go in parallel, don't forget, with the thing that you are actually measuring. Yeah, so they are going across. Yeah, they need to be potentially another route. In fact, the voltmeters have infinite resistance, so there is actually no current that can flow. But in theory, they are providing a route, so they are in parallel with those branches. So in those cases, you've got the same voltage across each of those components, whether it's the battery or each of those resistors X and Y. They've all got 9 volts in that case. Or they might have all been 3 volts, they might have all been 1 volt. So again, back to AQA's specification, quite a useful summary. For components connected in parallel, the potential difference across each component is the same. The same for each component. The total current through the whole circuit is the sum of the currents through the separate components. Similar to what I was saying about the junction. Yeah, the current going into that junction is the same as the total current coming out of that junction. So here's another example of what we've been talking about, just to make it absolutely clear. I've got 5 amps going into this junction here. If I had 3 amps going that way, hopefully you're shouting at me, telling me that the other junction, the other branch rather, would have 2 amps. Yeah, they must add up to the 5 amps. Don't forget also, it goes the other way too. So I've lost no current. Remember, this is in series. Yeah, this branch, there's no alternative route. So these are all in series. So the current here is the same as the current here. This is all in series with itself. So the current here is the same as the current here. When I reach this junction, what's going to happen? They are going to add together. Yeah, the current going into that junction must be the same as the current coming out. And so we should have 5 amps coming out of that. In other words, the same as what we started with. Advantages of parallel circuits then. Lots of advantages to parallel circuits. Usually, more often than not, you want to be able to control devices separately. So if you have these devices in parallel, in this case these lamps in parallel, then obviously I can control what's going on with each lamp. If I want to turn one off at different times, turning another one off, then I can control that. I'm allowing the current to flow through just this loop, whereas these loops, the current has been stopped by that switch. And I can turn that one on, and I can turn that one on. That's usually more useful. In a similar way, if this lamp breaks, I was talking about the Christmas tree lights earlier, if that one breaks, that's not going to stop these ones from working. Yeah, so I can allow the rest of my circuit to continue working. We talked about the series circuit. With the series circuit, because this voltage is shared, let's remind ourselves that this was 9 volts from the battery, then this would be 4.5 volts, and this would be 4.5 volts if they were exactly the same resistance. So we're losing energy for each of those lamps. Yeah, you're only getting a transfer of energy of 4.5 joules per coulomb. So these lamps are going to get dimmer, and as we add more lamps, it's going to be shared more thinly. So you're going to get dimmer and dimmer lights. But with parallel, remember the voltage across this again is 9 volts. The voltage across this is also 9 volts, 9 joules per coulomb. Across here is 9 volts, 9 joules per coulomb. And so these aren't going to get dimmer. Up to a certain extent, there are reasons why it doesn't go on forever, but up to a certain extent, as you add more lamps, they're not going to get dimmer. Now, you're not getting energy for free. Don't think that's breaking conservation of energy. Okay, it's not getting energy for free. But in terms of just pure brightness, you are going to get brighter lamps, and they're not going to get dimmer as you add more of them. That's super handy. So when connected in parallel, the lamps are brighter than connected in series, and they remain brighter. The lamps can be controlled individually with switches. If one lamp breaks, the others will continue to work. So a little recap, have a go at this question, see how you do. Here are the words you could use there. When components are connected together in series, they will all have the same current flowing through each of them. When components are connected in parallel to each other, they will all have the same voltage or potential difference. Lamps are usually connected in parallel to each other, as this allows them to be controlled individually by switches. And if one lamp blows, the others can still continue to operate. So we've looked at a similar example to this, but classic, straightforward exam question here. You've got a current going into this, a current produced by current in this branch here of 6 amps, and they're telling you that this branch has 2 amps. So what would the current going through this resistor here be? Hopefully you can see fairly straightforwardly that it will be 4 amps. Yeah, the 2 plus the 4 must equal 6. Here are some more examples. Have a go at these. Pause the video and I'll give you some answers in a second. So in this case, what we've got an ammeter in A1 here, a reading of 0.5 amps. Hopefully you know that in a series circuit, it's going to be the same in each of those. Don't forget my units. So they've got the units here already, but this is going to be 0.5, 0.5. If this was 1.0, they'd all be 1.0. As long as they're in series, they are all going to be the same, except that I've written that wrong. 1.5, 1.5. What is the current flowing through the resistor? In this case, the second example here, we've got 3 amps here coming into this junction. We've got 1 amp coming out of this junction, so we must have 2 amps going through this resistor. The resistor has a resistance of 10 ohms. What is the resistance of the bulb? Okay, well, that's a little bit more tricky to think about, but for now, just think about it kind of qualitatively. They're telling you that the resistance has a resistance of 10 ohms, and through that, you're getting 2 amps there. Through this lamp, we're getting just 1 amp. We're getting less current. So think about it. If there's less current, there must be a greater resistance. Yeah, you've got the same potential difference. They're in parallel. You're getting the same potential difference, the same push, but a smaller current. In fact, half the current. Therefore, the resistance must be double. Here's another question. Pause the video, have a go at those. So what's the current flowing into the junction here? Well, these two are in parallel. Yeah, there's a choice junction here. What's coming out of the junction must be equal to what's going into the junction. So we must have 5 amps, 1 plus 4, going into that junction. If the resistance of the variable resistor is increased, what will happen to the current in the variable resistor? So if we increase this resistance, what's going to happen to this current? Remember, resistance is trying to make it harder for those electrons to flow, or those coulombs to flow. So if this resistance increases, then this current is going to decrease. As a result of that, if the current is going to decrease through this one, but the total current is the same, then this is going to increase. Filling in the missing currents for these circuits, fairly straightforward again. Same idea. We've got 1 amp going into this junction, 0.6 coming out of it, so there must be 0.4 amps coming out. 0.4 going into this junction, 0.6 going into this junction. So again, we're back where we started with 1 amp there. And then finally, same idea, very similar, much easier actually. 5 amps going into it, 2 amps going through this branch, so we will have 3 amps going through that branch. Then with potential differences, we've got our series circuit here, 6 volts across here. It's going to be 6 volts across there. Yeah, these are in series with each other, but they're also potentially in parallel. Whatever this potential difference is, it's going to be the same across that component. 3 volts here. This time we've got series circuit, but they are split. Therefore, they are split rather. So the series circuit, the voltage is going to split. We've got 6 volts going to split between the 4 volts and the 2 volts. So this plus this must equal this. Similarly, this plus this, they're in series. So the total potential difference is 4.5 volts. Assuming these two lamps are the same, we've got our 6 volts here. So if they are the same resistance, then they will split equally. If they weren't the same resistance, they might not split equally. Again, these resistors here, I think we're assuming they are the same resistance. Therefore, this must also be 3 volts, and therefore this must be 6 volts. Don't forget, though, that if these had different resistances, these are these lamps or these resistors, then the voltages might not be shared equally, but they would still total the battery voltage. And then with potential difference across parallel circuits, look at the circuit on the right. What is the voltage across the resistor and the lamp? Again, hopefully straightforward. In parallel circuits, the voltage is the same across each component. So it's going to be the same. 5 volts, 5 volts. Same again. These are also in parallel, just drawn slightly differently, but these are also in parallel with each other. So this is going to be 4.5 volts and 4.5 volts. Okay, the final thing we're going to look at in this video is resistances in series and parallel circuits. If you have 2 resistors in series, clearly these are in series. There's only one loop that the current could go through. All you need to do is add up those resistors. Okay, so if we knew that this first resistor was 3 ohms and the second resistor was 2 ohms, the total resistance, I could effectively replace that circuit with something that looked like this. I could replace those 2 resistances, 2 resistors even, with 5 ohm resistor. That's the equivalent. Those 2 circuits are equivalent. So as you add more resistors in series, the resistance increases. And yeah, there's the circuit there. There's a formula you do need to be aware of. R total is R1 plus R2 plus R3 plus R4. You could keep going. You could keep adding more resistors in series, and that's how you work it out. In parallel, you don't need to know a formula, but you do need to know a pattern. Again, it sounds counterintuitive. Quite often with parallel circuits, it doesn't quite feel as intuitive as with series circuits. But as you add more resistors, in fact, what's going to happen is the resistance of the complete circuit is going to go down. So you don't need to know the actual maths of it, but if I replace those 2 resistors in parallel with a single resistor, as I add more resistors to it, I could add another one. I could add another 10 ohm resistor. The first thing to be aware of is as I add more, this resistance, the total resistance, is going to go down. So the total resistance of 2 resistors, here's the final thing, so I should say, as you add more resistors in parallel, the total resistance goes down. The second thing to be aware of, and this is a really useful thing to know, the total resistance of the 2 resistors is less than the resistance of the smallest individual resistor. Okay, so you don't need to know the actual value, but if you look at these 2 resistors, 3 ohms and 10 ohms, the combined resistance of those, if I replace them just with one resistor, the resistance of this would be less than the resistance of the smallest individual resistor. In other words, it's going to be less than 3 ohms. And that is counterintuitive. Yeah, as you add more resistors, I could add another 10 ohm resistor. I'm adding more and more resistances to this, but it's never going to be bigger than the smallest resistance I've got in this circuit. And that does come up occasionally, and it's really useful for all exam boards. Although it's specifically mentioned in AQA, it's a really useful thing to have in your mind for other specifications as well. So a little summary of the rules here. I've resisted giving you green screen stuff to note down. Hopefully you've been thinking hard about all the ideas I've been talking about. But in terms of your notes, again, it's just taken directly. I've put these up before, but they're just taken directly from the AQA specification. All of these points are relevant for all specifications, but I think AQA puts them in a way which is really clear. So make a note of those if you need. Have a think about them, go back into the video, have a look at PhET, work through some of those ideas to really get a feel for how it works. And hopefully, after all of that, you should be able to describe series and parallel circuits, explain and calculate the current and potential difference in series and parallel circuits, describe and calculate how resistances combine in series and parallel circuits, and be able to think about and state and explain advantages and disadvantages of series and parallel circuits. Hope that's been useful. Look out for new videos. I think I've got one more, maybe two more coming for electricity as soon as I can, and there'll be more coming very soon. Cheers everyone, have a good day.